Today I want to talk about very practical application of diffusion models, how we can use it not only for entertaining images generation, but for solving real problems. In our case, it's discriminative CNN training. And I'll show you how I used diffusion models for solving very specific problems. It's 3D human body pose estimation. We really had such problems in our company. Today talk will be more engineering than research. At first, let me a little bit talk about what we are doing in Vona. We do augmented reality experience with fashion things like clothes, footwear, watches, and others and others and others. And that means that we need really specific labeling. It's not so trivial kind of labels, so it's not enough to predict just 2D key points. We need some kind of 3D data to work very efficiently with such tasks. And also we should run our models on mobile devices in real time. That means that models should be really small, ideally several megabytes. It should have possibility to run as 30 FPS. So we have really a lot of constraints here, and that means that we need really qualitative data to train such small models, such as it's much harder to train small models in comparing with huge models, and the data should be really qualitative, labels should be really qualitative, and I want to talk how we can try to obtain such kind of data using diffusion models. At first, let's talk about foundation models, especially foundation models in computer vision area. Why about foundation models? Because it models which allow us to don't solve new tasks from scratch. We can use some knowledge base which stored in such models, and it's really awesome. Maybe main properties of foundation models that were trained on really diverse datasets, very huge datasets. They usually trained for one task and can be used for specific tasks you need. It's also last time it's really almost impossible to reproduce such models training, especially if you are medium-sized company, maybe big company with huge computational resources can allow it, but if you have, I don't know, maybe 10, 20 GPU machines for all your company, it's almost not impossible to train such model. Also, such models usually have great generalization capabilities and can be used even without fine-tuning, such as, I don't know, Stable Diffusion and a lot of another models. Most popular computer vision foundation models are CLIP. We'll talk about it a little bit later, but it's also a part of Stable Diffusion approach. It's pretty maybe familiar to every engineer who works with Stable Diffusion. It's about matching of encodings between images and text descriptions. It's open source model by OpenAI. Another one foundation model is DALI 2. Of course, it's not available for open source usage. You can find, as I know, only after encoder for this model, but still it's one of the first text-to-image model, and according to their paper, they have really great quality of generated images. And one of really interesting thing from last year, it's a segment anything. It's a really awesome thing, especially if you need to solve some segmentation problems. It's a segmentation based on open vocabulary. You can just select some bounding boxes, key points, and or just segment all you see, and get really qualitative segmentations, almost pixel perfect masks. And similar to segment anything, another one model is ground in Dino, where it works a very similar way. You just give an image, raw image, and can obtain bounding boxes. For open vocabulary, you can ask to find anything you can describe with text. And it also works really well. Okay, and now let's talk more about Stable Diffusion, because Stable Diffusion is really only one available open source model we can use for images generation. It's a pretty qualitative model. We have so much fine-tuned, trained Stable Diffusion models from different companies, from AI enthusiasts, and you can find really almost anything you need. Okay, in previous talk, it already was described how Stable Diffusion works under the hood. Let me recap a little bit. We have a clip model. As I said, the clip model helps us to tokenize text to get some text embeddings. After that, we generate some image in latent space. It's just a Gaussian noise. Yes, it's our latence. It's much easier for Stable Diffusion to work with in latent space than with RGB images. And after that, we just perform several denoising steps using UNet network. We need to know how to schedule this denoising for UNet. And when we already have denoised latence, we use variational autoencoder to decode our image and get pretty cool image of dog. Why I think that is of course, a foundation model, because it's trained on really huge datasets. It's Leon 5B, but really it contains almost 6 billion of text image pairs. It's trained for text-to-image generation task, and you really need very huge amount of computation to train a diffusion model from scratch. It's approximately 150,000 GPU hours, as you see. With cost, it's obviously not possible to train it at home. You can train it if you are a medium-sized company, and all things you can do is just fine-tune already trained diffusion models. And of course, Stable Diffusion has pretty good understanding how the world looks like. It knows a lot of things about world, how people looks like, how animals look like, so we can generate really diverse images using Stable Diffusion. But text-to-image is not so it's not enough really fast, because usually we want much more than just image generation by text description, and with some tricks we can do it using Stable Diffusion. We can do such things as super resolution in painting, cloud painting, 3D models generation. This area is really experimental now, but it's really so interesting. You can read more papers about it. Some kind of art generation. On Reddit you can find a lot of really amazing arts. Pipelines usually are pretty complicated, but it's still amazing that using AI you can generate such cool things. And also very interesting maybe area, it's video games assets generation. You can generate cube maps for surrounding textures, also 3D models and other things. Okay, but problem we really have with vanilla Stable Diffusion, that it's not trivial to force it generate what you really need. It's not so trivial only using text to describe what you really need. So I want to talk more about ControlNet, how ControlNet can be used for Stable Diffusion generation, to control Stable Diffusion. Here is very simple example. I generated a rubber duck in River Thames. All looks pretty good, but let's imagine that I want another point of view for any reason. And I add to description that I need a top-down view from the left side of the duck. It really, surprise, surprise, it really generated a top-down view. But now duck looks like some boat. It's not so cute now. Yeah, maybe we can try to fix it. We can try to add some negative prompt, like it shouldn't look like boat, it should be cute, it should be yellow. Okay, now it works, but it totally ignores part about top-down view from the left side. So for such purpose, we can try to use kind of kind of sketch. Yes, it's my personal art. As you can see, I'm not an artist at all. But I draw such sketch, and it was used by ControlNet to generate this duck, and I don't know, maybe I'm pretty satisfied with it. How does it work? Also very fast recaption. For ControlNet we can use almost any control, but in vanilla ControlNet, usually it's kind of edges, head edges, canny edges, some depths, normal map information, scribbles, as an example before, or maybe open pose, human body representation. But really you can use almost any control. And even it shouldn't be image, it shouldn't be 3 channels image as in vanilla ControlNet, but of course it's not so trivial, and you should write some additional code at top of ControlNet library. Here is a simple, I don't know. Okay, here is an example of how Stable Diffusion pipeline looks like in ConfUI library. I usually use it for quick prototyping if I need to generate something very simple, and also I have here a possibility in real time see how latence looks like after different denoising steps. It's for here is text encodings, positive, negative prompts, denoising process, and image saving. Okay, and really control net pipeline is pretty similar. We should only add our control to the denoising process. It's additional information for control net cross-attention mechanism. So control net can use it for content specification. Internal, it's also internally it works also pretty easy. We don't fine-tune original weights of our basic stable diffusion model. We create a trainable copy of these weights, and we add zero convolutions before and after our trainable copy. Zero convolution, it's a pretty easy concept, just a convolution initialized with zero weights. That means that on the first forward propagation we will get results only by original layer, but after several steps gradually we will change the way how stable diffusion generate images, and it helps stable diffusion not to overfit, especially if you have not a huge amount of data. You can use such concept for really small data sets. You can fine-tune stable diffusion in such way using, I don't know, maybe 100 images can be enough. Our control here is C. We just mix it to original layer input. Also applying zero convolution between original input and our control encodings. Okay, now let's talk about data we need, data we want to generate, and why sometimes some kind of data can be really hard to label. For example, we have really trivial, maybe we can call them already solved problems. It's like classification, segmentation, 2D human pulse estimation. I call it a trivial labeling because it's pretty obvious how to label such data. There are a lot of open source tools we can use for such labeling. It's pretty easy to use crowdsourcing platform to label such data, and process of labeling is very trivial. I remember, I don't know, maybe 2-3 years ago, when I need, I don't know, maybe some little classification data set, I just labeled it for 2-3 hours because it's much faster than create labels task on some crowdsourcing platform. It's also a variant. But from other side, we have non-trivial labeling for some tasks. Of course, it's almost in computer vision, it's almost always about some 3D information, because it's not obvious how to if you have image of squirrel, it is not obvious how to label a depth map for this image. And also it's a 3D pulse estimation, 3D object detection. And here are points why it's so hard, because the really ground truth labels can be obtained only in a laboratory environment. That means that such data set will have a really poor diversity. Also, there are no good available open source tools for such tasks, for such data labeling. we have problems with manual labeling consistency. If two people will try to label some 3D pose, and after that you will try to compare their labels, it almost always will have really poor consistency. It's also about slow labeling process. It's very hard to learn labelers, people who label data manually, how to label such data. You need some additional steps of verification after such process, after labeling. As a result, it's almost impossible to use crowd-sourcing platforms like mTorque, Scale AI, like this, and also as a result, we have a pretty big price per image per label. How we can use here Stable Diffusion and Control Net to avoid such problems, to get really qualitative data sets with non-trivial labels. From the one side, Stable Diffusion knows a lot about how world looks like. It can generate very diverse images. From other side, using Control Net, we can control and apply some conditions to our image generation process, and as a result we can get diverse images which satisfies our condition, and that means that it satisfies our labels. Okay, and now about our specific task we have. It's a clothing try-on, side view try-on of garment. It's a really not so trivial task to label data for, because we need not only 3D body, skeleton, 3D points representation, but also we need some volumetric representation of our person to have information how we should fit specific clothing, how it should look like on specific person. That means that we need something, some volumetric representation. We need such kind of labels. We need, at first we need some kind of 3D key points data, and in addition to this we need some volumetric information about human body. So it's really hard to task, hard to label. Okay, and one moment to clarify, to solve this problem, in our company we have some specific internal representation of human body. It's not SMPL, because SMPL should be licensed, and it's not so cheap really, but it's pretty easy to create a very similar representation of human body, which pretty good works for us. Okay, and let's start from data we have. At first we have a big amount of short side view videos. We collected such videos using crowdsourcing platform. It's really cheap. I highly recommend all people who need to collect some kind of data try to use crowdsourcing platform for collecting videos. It's really cheap. And from other side we have a small amount of 3D labels. We created our internal tool to label such images manually, to label a 3D representation of human body manually, but process is really hard. It's really hard to learn people how to label such data. It's really hard to verify such data, really hard to get consistent labels for same image, for example, from different labelers. And also process is very slow, very slow. So we need to think about some ways how we can generate data using Stable Diffusion. We can take Stable Diffusion, attach ControlNet framework on top of it and fine-tune using our already labeled samples and try to generate new samples using ControlNet and train our network. Here is a very schematic illustration. How does it work? We need 3 kinds of input. From left side we need some control to enforce stable diffusion, generate images which satisfy our labels. From the other side we need text description for these images. So even if you use ControlNet, text description still is very important. You can't ignore it. And of course we need images. And if we have all 3 inputs, we can fine-tune our ControlNet and try to generate new images from this distribution. Okay, let's start from text description. Text description obtaining is very trivial. We can use such tool as clip interrogator. It works on a clip model, and you can really easily obtain text description of any image you have. It works maybe 2-3 seconds per image, and if you have, I don't know, several thousands of images, it's not so long to generate text description for all these images. Okay, now let's think about controls we can use for our data generation. Of course, ControlNet already have some pre-trained ControlNet extensions based on open pose human body representation. But here I just generated images based on the same open pose control, and as you can see, it is not ideal at all. At first they look not so realistic. Length of arm here is very strange, and poses are not consistent between images. And here one more example. Especially here you can see that arm is very different from original control, and also something happened with limbs length. Yeah, here. So we should think about something different. It's pretty. It's easy to understand why such kind of control is not so good for 3D pose generation, because 2D information is not enough to generate corresponding 3D image. It's always some inconsistency. So we can think about some other controls. For example, here like head edges, and but with head edges we has another problem. Here on the left side you can see original images. On the top you can see head controls for these images, and on the right side you can see images generated based on these controls. And as you can see, that model overfitted a lot. We can understand it, for example, by flowers on the wall. We have flowers here, we have flowers here, but we have no flowers on our control. That means that our model was overfitted for specific images, and that means that we will have really poor diversity for our generated data. But poses here are pretty good, realism so-so. That means that we have some kind of trade-off. We have a trade-off between realism, maybe between how our data realistic, how it's about diversity of this data and trade-off between how our data corresponds to our 3D labels. So we should find something intermediate, some intermediate control for it. I tried a lot of variants really. For example, here is combination of edges and open poles, and as you can see, it's also overfitted a lot because images are really similar. It's a really bad sign. And the best variant I found, it's a control which looks like here. In the next slide I will describe what does it mean. And all these images, they are synthetic. It's not real images, and it was pretty enough for our task, for me, because they look pretty realistic from the one side. From the other side, this control preserves our 3D pose. And diversity also is pretty good. We have very diverse images, and I think that it's awesome. And about this data representation, about this control, it's very similar to dense pose, but not original dense pose. It's about continuous dense pose representation. If you are familiar with dense pose paper, you can find its implementation in Detectron GitHub repository. It just UV mapping between 2D pixels and 3D model. And our representation we used is just a continuous version of dense pose, and it works pretty effectively. Okay, now about results. Before synthetic data generation, we had something like 10,000 of labeled images, a lot of unlabeled images. Our main metric was APE. It's mean pad joint position error, just absolute error for every joint. Of course, we have some another perceptual metric to validate results. And after generation, we had a data set 200,000 labeled images, and a metric was improved dramatically. So it's a really cool result for us. One more moment for such generation. Of course, it's almost impossible to enforce a stable diffusion model to generate always qualitative images, because from time to time it's tried to generate extra limbs and things like this very inconsistent human pose. So we need some solution how to get rid of such bad samples, bad examples, and solution was really simple. Really, we can use some well-trained 2D key point predictor. We can on every image we can try to predict 2D pose and calculate distances between corresponding joints for every image, and if distance between label and predicted 2D points. And if distance is too high, we just get rid of such samples. We think that it's a bad sample, and according to my calculation, it was something like 10% of such images, so it's a very important step to do after synthetic data generation. Okay, and maybe at the end, let's talk more about other ways we can use stable diffusion for other tasks to generate data. We can use stable diffusion for classification problems. It's pretty obvious how to use it. For example, if we need to classify garment, we want to train model which classifies garment types, for example, skirt, t-shirt, etc. We can ask Stable Diffusion to generate images for with labels, but it also, of course, requires some work with prompts, with prompts engineering. And one more interesting variant is to use for segmentation problem solving. It's a really composition of foundation models we can use here. As the first step, we can generate raw image. After that, using ground Indina, we can ask ground Indina to find labels we are interested in, and after that we can use bounding boxes for segment anything and get really qualitative segmentation masks. And it's really awesome. It's speed up iterations really efficiently, because from scratch you can obtain image with pixel perfect segmentation mask. It's awesome. And you even don't need to do it yourself. To combine all these tools, you can use already existing library, grounded segment anything. It do all these things instead of you. You can just make text prompts, ask about some labels to find, and as a result get segmentation masks. Conclusions about my talk. Of course, we have pros and cons for such method. Let's start from pros. Maybe the main pros, of course, it's a fast iteration, fast prototyping. You can validate your idea really quickly. For example, if you need to, segment some data set, you at first need collect data. You also can have problems with this. For example, if you need some sensitive data like people faces, you should care about legal issues, but using Stable Diffusion you can just generate people, and it's much faster than launch a full labeling process with validation and all. Okay, and we need no data collections, and it's almost free. And also it can help with complex labels, because as I showed before, sometimes it's not so easy to label a lot of data, even if you have a tool for it, even if you have people who can label, because it can be really slow and inconsistent. And cons from the other side, there are no universal solutions for synthetic data generation. You still need to spend some time to find ideal text prompts, to find ideal controls for ControlNet. You should spend some computational resources to generate images. It's also not so fast. Generation such as it computationally expensive, it can take 5-10 seconds per image. Image is not a big resolution, but such as we work with convolution networks, 500s on 500s, it's pretty enough for almost all tasks. And you still need, as I said, you still need to work with prompts, and it will be better to make some post-processing after generation. And maybe the main cons that really, sadly, it can't replace fully traditional way to collect and label data, because your distribution of data generated by Stable Diffusion will be shifted. It will not represent your real data distribution as well as real data you can collect, and also labels can be not so qualitative for all tasks. So it's not a real replacement for quality, but it's a very good replacement, as I said, for fast prototyping, for quick iteration, for your ideas, fast validation. Okay, I think that's all. I'm ready to answer your questions.
So you're talking about labeling human models, like labeling humans to get 3D models of humans.
Yeah.
To use, maybe I missed that part, to use the estimation to do, like is a pre-labeling method to...
Pre-labeling method, like instead of labeling from scratch, try to predict pose, and after that label only bad predicted images. Do you mean it?
Because there are methods which are like actually you're providing the image, you're providing the depth estimation of corresponding image, and the model gives outputs a 3D model of the object. And interesting fact is, like iPhones 13 Pro or 14 Pro have LiDAR sensor, so it can just on the photo attach predict the depth.
Really, we tried to make some pre-processing for labeling process. We tried to improve it as we can. We tried to predict at first images, and after that labelers, they also need to select only bad labeled images and label it manually, but it's still pretty slowly.
Yeah, okay. And our question is like, what kind of stable diffusion model would you suggest to predict from one perspective, the other perspective, like from left field and the right field? Like you have a left view image and you want to predict the right view perspective of the image. What?
Maybe it's hard to talk about stable diffusion as some predictor for different point of views, because it's really not so trivial task, and it really may be more about some 3D models generation. As I said before, stable diffusion can be used for 3D assets generation, 3D models generation, and in most of papers, researchers use very similar approach. They try to generate images using stable diffusion from different point of view, and after that merge into one 3D model, but it works not so effective in most of cases.
Except this filtration method that you use, that you compare the sizes of the body parts,
yeah,
the distances. Do you have also some examples that, let's say, the part of the body was misshaped, or like there was, let's say, increase or decrease of the size? That could also.
Yeah. I understand you. It's a good question. It's also can be problems that all your joints can be on the right places, but size of parts of body can be really different in label and in generated image, and you also can try to use something like segment anything model to validate not only 2D points correspondences, but also calculate intersection of a reunion, for example, for corresponding parts of a person. Yeah. It's also a good idea for post-validation.
I wanted to ask about how did you decide on the size of the synthetic data set? Did you try to overflow it with it, or just choose very specific high quality ones?
You mean about how I decided to generate 200 or thousands images? Yeah, really, if you already have qualitative model, it's not a problem for you to generate such much images as you want, because maybe the main part here is to obtain such model, and it was something about 2 days on several servers to generate several hundreds of thousands images. So really, then more images, quality can improve, but not so dramatically. You can try to build some kind of learning curve, but maybe it will be just easy to generate such much images as you can generate. Yep.
Yeah, and a quick follow-up one, do you treat them differently during the fine-tuning, or do you treat like synthetic and real images exactly the same? Or like, I don't know, sampling weights or whatever?
Do you mean during... okay, I got the idea. Because we use same weights, but it's also a kind of improvement we can use for... we can assume that labels manually labeled, they are better than synthetically generated, but I like to see into data, and I see that generated results and original results, they were pretty similar to each other, and I decided that it's not so important to make some weighting between them.
Yeah.
Thank you.